Hey, what's up, guys? Okay, so this video is about interesting proof that I recently saw, and I think it's interesting. So share with you guys. So this is the Furstenberg proof of their infinite primes. Okay, so this proof is not difficult, but blow my mind. Okay, so basically this is so-called using. So basic idea is that using topology. So using topology to show their infinite primes. And by the way, recently my YouTube channel just got accepted in the monetization. So thank you guys. Okay, so hope you guys subscribe to my channel. So before I start, let me just quickly review the stand. I mean, there are various proofs. There are infinite primes, right? So you have like 2, like 3, like 5, like 7. So they're infinite, right? So the go back to the 2000 years ago, the standard proof is basically proved by oscillate, or I think oscillate, right? So you start from P1 up to Pn, and then just plus 1, right? And you can check that if your prime is finite, then this guy plus 1 will not be divisible by any prime. So this guy must be prime. Okay, and the second proof, which is also you can use analytic number theory and use the Mertens theorem, so you can prove that if p less or equal to x, 1 over p is approximate log x. And I think plus 0.1 or something. So you can use analytic number theory to prove it. So this one that need more work. And also there's Erdős theorem. So basically using it's not difficult. And there are another proof which is interesting. You can consider the Fn is 2 to the 2n plus 1. This is called the Fermat number. And you can check that the GCD of the both of the distinct Fermat number has no common factor. Sorry, it's 1. Okay, so they're always coprime. Okay, so there are infinite Fermat numbers, so they're infinite prime. Okay, so these are like 4 proofs that they're infinite primes. If you want to see this, I will post my video below, so you can check if you want to see more proof. But this proof using the basic topology, so it's crazy, so very crazy. So let's go through a proof. Okay, so I'll consider x is just the integer, and what we're gonna do is define a open set. Right? So in the topology, that the first step is you need to define which subset is open set. So this is like a standard step. And so define U subset is open. Your subset of the Z is open if 1 or 2 holds. If satisfy or 2 or 1 or 2. Okay, the first one is that if U is empty or trivial. Okay, the second one is that U is a union. We just write a union. Okay, so very bad notation. So let me just use union. Let me just use union. Let me just using this just union of SAB. Okay, so union where A is not 0. Okay, so I haven't defined SAB, so let me just quickly say, so SAB will be just very simple, just AZ plus B where A is not 0. Okay, so what this means is just that you start from A, right, and then you get 2A and then 3A. So you just put A plus B, so A plus B is where you want, and 2A plus B, and 3A plus B. So just the arithmetic progressions. Simply speaking, it's arithmetic progressions. Okay, and the difference is A and the start from B. Okay, so still beat it, for example, to 0 is just 2Z, right? So just the odd or even, and as to 1 are just all odd. Okay, so this guy you can basically write as a B mod A. So all the integer which is B mod A. Okay, so U is the union of this guy, A is non-zero, then this is called this is defined to be open. Okay, so the next step is that we hope to show, or this is like a simple exercise, right? So you need to show that this x is this is a topological space. Okay, in order to prove this, right, you need to prove that the axis, right, axis and empty are both open. So x is open, right, because I can write as to be 1, 0. Okay, so just see. Okay, and the U by definition, the empty set is open. Okay, so this is true. Now we need to do the finite, the countable union, right? So countable union. Okay, so it's open is trivial, right? Because I already defined my open sets the union of arithmetic progressions, right? So if you give me countable union, it's always countable union of arithmetic progression. Okay, so third one is the finite intersection. Okay, in order to prove this, I guess we only need to like prove the two intersection, right? So okay, so basically we just need to show, right? If I give you A1, B1 intersection A2, B2, they will still be S something or empty. Okay, if it's empty is fine, right? Because for example, this is even number and odd number, right? So they can be empty. Empty is fine, right? Empty is open. Okay, so we don't care about this case. Let's consider this. And this is very, very simple, right? This is just the Chinese remainder theorem. Okay, so Chinese remainder theorem, hope you guys know it. So for example, it's just x1 equals to a1 mod b1 mod a1, and x equals to b2 mod a2. And ask you about the intersection, right? So if a1 is a2 are not coprime, if they are coprime, if they are not coprime, then you basically what this Chinese remainder theorem tell you that if there is a solution, the solution must start from x0 with some initial solution, and the mod the list common multiple. Okay, so the proof is simple, right? Because obviously that if there is an intersection, obviously if there is a non-trivial intersection, there at least one point, then the mod LCM A1, A2 will become these two solutions. If there's a solution here, then there must be the smallest which is close to 0, positive. Okay, that one that you call that one x naught, you call that one x0, then you can prove this. This is simple proof. So you can check the Chinese remainder theorem. Okay, so we prove this is topological space. So what's next? Okay, so the next is weird. Okay. So the fact of this, the first one is that the finite set cannot be open. Okay. The reason is that all the open set are infinite, right? Are infinite point, contains infinite point. Okay, unless it's empty. Okay, so if you have any finite set, this cannot be open. Okay, so this is equivalent to the Z module cancel any finite points, cannot be closed. Okay, cannot be closed subset, cannot be closed set. Okay. The second one is that the SAB are both open and closed. Okay, by definition, it's open trivial, but what is closed, right? So you just easily check. SAB basically just the Z cancel SA, B plus J, and J from like 1 to A minus 1. Okay, so this is stupid, right? It just tell me that if I start from A plus B, and I only need to I collect every point which is A plus B and 2A plus B and 3A plus B. This is the same as I just auto integer Z, and I cancel these points, right? Cancel A, all the multiple A. I cancel this, and I cancel all the multiple A plus 1. Okay, until that I get J equals to A plus until I get J to be A minus 1. Okay, so it's B plus A minus 1. Okay, so I just I go to like okay, maybe this is not good illustration. So first, okay, so let me just do this. So first I kill j equals to 1, right? So I kill the sb plus 1, right? And I kill sb plus 2, and I keep going, right? Kill ab plus a minus 1. So basically I start from a plus b, and I kill this point, 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 until we reach another another set, b plus a minus 1. Okay, b is here. B plus a yeah b plus a minus 1 is here, right? So I kill all the points up to here. Okay, so basically the idea is basically I just kill all the points from like one interval, and the remaining 1 point, which is just this b. Okay, you can draw on the plot. Should be simple. Okay, so once we have this, then we are going to prove the results. Okay, so theorem, there are infinite primes. Okay, the proof goes as follows, right? You go z minus plus or minus, right? So by as a set, let me just using a set notation. So as a set, right? As a set, this guy is what? This guy is like by our results, right? So you know that prime is like every integer has the unique prime factorization. So all this basically is definite union of all s at p0, right? Because any integer is except for plus or minus 1 can be represented as a product of primes, right? So this must be prime. Okay. Okay, it will take all the prime, right? And it must be the multiple prime. Okay, and so the fact 1 tell me that this is closed, right? This finite point, so the left hand side cannot be closed. Okay, so suppose, but suppose there are finite prime. Suppose there are finite prime. Then RJs, right? This SP0 will each SP0 will be open, will be closed. Okay, but now then RJs will be finite union of closed set. Implies that RJs is closed, right? Because finite closed set is always closed. Contradiction. Finite union of closed set is closed, right? So, but we know that RJs cannot be closed, so that means that there must be infinite primes. Okay, so here must be infinite. Okay, so this is the proof. Yeah, this proof is interesting. I don't know. I don't have any comment for this proof. I mean, it's amazing. Okay, so see you guys next videos.